Hello mathematicians, thanks for joining me again today. We're going to be looking at limits, and so what I want to do first is find the limit as x goes to 1 and natural log of x over x minus 1. So now what we want to do is we think about limits is the first thing we should do is we should evaluate at 1 and see what this looks like. Now if I plug in 1 I get natural log of 1 over 1 minus 1 is natural log of 1 is 0. 1 minus 1 is 0, so I get 0 over 0. Now if we look at this, I can't divide by 0, so this is not defined, so this would not be a continuous function at the point 1, so I can't just plug in 1 and get out an answer. If I had gotten a number out up here, like 2 or 3 or even 0, I would be fine, but because I get something over 0, it's undefined. Now, just as a reminder, if I had gotten a number over 0, that would mean that as we're getting close to 1, this is going to get close to a number, and this is getting extremely small, so the entire fraction gets extremely large. So we would either have positive or negative infinity, because there would be a vertical asymptote there. So now the interesting point is when I have 0 over 0, because that is an indeterminate form, which means that this limit can be anything. We don't know what it is, we have to do more work. So now as we do more work, in the past we've had to do things like factoring, or multiplying by a conjugate, or finding a common denominator to combine fractions. But what we've just learned is L'Hopital's rule, and what L'Hopital's rule says is that if we're going to take the limit as x goes to c of f of x over g of x, and when we plug in c we get this 0 over 0, then what we can do instead is we can take the limit as x goes to c of f prime of x over g prime of x. That is, I can take the derivative of the top and the derivative of the bottom and take the limit thereof, and I should get the same answer as long as I got the 0 over 0 form. Or we'll also look at infinity over infinity. And so if we get one of those indeterminate forms, we're allowed to use L'Hopital's rule. Notice that if we got a number out, we can't use L'Hopital's rule because it doesn't work. But if we got a number out, we would be done because we would have a continuous function, so we would have the limit. If we get a number over 0, we can't use L'Hopital's rule, but we just decided that that would be a vertical asymptote, so our limit would not exist. So really the only interesting point is when we get a 0 over 0, so then we can use L'Hopital's rule for those cases. Because we get 0 over 0, we can use L'Hopital's rule, so what we find is that this is going to be equal to the limit as x goes to 1 of the derivative of natural log of x is 1 over x. And the derivative of x minus 1 is just 1 minus 0 is 1. And so what we get here is, this is the limit as x goes to 1 of 1 over x over 1. We'll simplify into 1 over x. Now what we've been able to do using L'Hopital's rule is turn this seemingly complicated limit into an easier limit. And so now I have a new limit to evaluate, so I'm going to start the process over again. So I'm just going to evaluate this function at 1. So if I plug 1 in, I get 1 over 1. Well, 1 over 1 is just 1. That's a number. Therefore, my limit exists, and it's equal to 1. So I have now evaluated this limit. That is, the limit as x goes to 1 of natural log of x over x minus 1 is indeed equal to 1. Get another limit. And so as we calculate this limit, again, as we do with limits, we want to evaluate at the point 0 to see what happens. So if I plug 0 in for x, what I have is cosine of 0 is 1 minus 1 all over 0 squared, and we end up with something that looks like 0 over 0. So what we've seen now is that because we have the indeterminate form 0 over 0, we don't know what we're going to get, but we can use L'Hopital's rule to find what this limit is going to be. So what's going to happen is, if I want to find the limit as x goes to 0 of this, I can take the derivative of the top over the derivative of the bottom. So the derivative of cosine is negative sine. So I get negative sine here. And the derivative of negative 1 is 0. So I'm just left with negative sine of x is the derivative of the top. On the bottom, the derivative of x squared is 2x. So I get negative sine of x over 2x. And so if I want to find the limit of cosine x minus 1 over x squared, I can instead find the limit of negative sine of x over 2x. So I've taken one limit and I found a hopefully simpler limit that I can calculate. So we're going to start the process over again, which means that we're going to substitute 0 into the function and see what happens. If we do that, we get negative sine of 0. Sine of 0 is 0. Over 2 times 0 is 0. So again, we get 0 over 0, which is an indeterminate form. So it means we have to do more work. Well, as opposed to despairing and giving up at this point, we should note that, well, 0 over 0 means we can use L'Hopital's rule again. So instead of giving up, we're going to use L'Hopital's rule again. In that case, we get the limit as x goes to 0 of the derivative of sine is cosine, so the derivative of negative sine is negative cosine. And the derivative of 2x is 2. So now we have the limit as x goes to 0 of negative cosine of x over 2. Again, we've taken one limit and converted it into another using L'Hopital's rule. So we're going to try to evaluate it by evaluating at 0 and see what happens. So if we do that this time, we get negative cosine of 0 is 1. So we get negative 1 over 2 is negative 1/2. Notice now that we have a number, that means that we've calculated this limit is just going to be negative 1/2 because we got a number out. That means that's continuous at this point, so we can just substitute it in. So we're able to calculate this limit, which means we were able to calculate these limits. And so in the end, we get the limit as x goes to 0, cosine x minus 1 over x squared is just going to be negative 1/2. Now, just as a point here, I do need to check each time. I don't want to get carried away and keep using L'Hopital's rule, because if I try to use it here, I would get the derivative of negative cosine is sine, derivative of 2 is 0, sine over 0 is something over 0 is going to be undefined, and so we get a completely different answer here in that case. So that means what I'm trying to point out here is that you do need to be careful. You need to check each time what this is going to be. And we can only use L'Hopital's rule if we get one of these indeterminate forms. Again, as we look at another limit. And so, again, if we crawl back to our other examples of limits, what we need to do is figure out what's happening at the point. So I'm going to but imagine what happens as x gets large. So if I go off towards infinity, what ends up happening is x goes off towards infinity. And natural log of 1 plus 2 over infinity is going to look like infinity times natural log of 1 plus 0. And so what I end up getting is infinity times natural log of 1 is 0. So in this case, I get infinity times 0. Well, what is infinity times 0? Well, that is indeterminate. We don't know what that is as a limit, so that could be anything. We really don't know, so we have to do more work. So when we run into these indeterminate forms, we've seen that we've been using L'Hopital's rule, but L'Hopital's rule only works for the forms 0 over 0 and plus or minus infinity over plus or minus infinity. So that is, if we have a quotient, we're able to use L'Hopital's rule, but it doesn't say anything about a product. So we're stuck here not being able to directly use it. So instead what we're going to do is realize that, well, if I have a product, I can rewrite that as a quotient by dividing by the reciprocal instead of multiplying by the function. And so what I'm going to do is I'm going to take one of these functions and put them on the bottom. Now the easier one to do here is between x and natural log of 1 plus 2 over x. Looks like the easier one to do would be x. And so I'm going to move that to the bottom by rewriting this as the limit as x goes towards infinity, a natural log of 1 plus 2 over x. Now, if I divide by 1 over x, that's the same thing as multiplying by 1 over x, which is indeed just x. So I haven't changed the problem, I've just rewritten it so that it looks like a quotient instead of a product. Now that I've done that, again, I want to see what happens as x gets large. And if I do this again, I get natural log of 1 plus 0 is natural log of 1, which is just 0. And then 1 over a huge number is an extremely small number is 0. So, and now that I have rewritten it, I have my 0 over 0, so I can indeed use L'Hopital's rule. So now if I want to use the L'Hopital's rule, what that says is that this limit is equal to the limit of the derivative of the top over the derivative of the bottom. So I'm going to take the limit as x goes towards infinity. Now, these are a little bit more complicated derivatives. They're not terribly difficult, but because they're a little more complicated, I'm going to go off to the side and do this and try to, instead of trying to do it all in my head. So if I try to find the derivative of natural log of 1 plus 2 over x, what I would notice here is that, well, what's happening is this is a chain rule. I have an outside and an inside function. My inside function is the 1 plus 2 over x. My outside function is natural log of the inside. So the derivative of natural log is 1 over the inside. And the derivative of 1 plus 2 over x is 1 plus the derivative of 2 over x. Well, now if we look at the derivative of 2 over x, I'm going to take that to the side just to remind myself of what's going on here. This is really 2x to the negative 1, because instead of dividing by x, I can multiply by x to the negative 1. Therefore, I can use a power rule here. So I get negative 2x to the negative 2. And so, if I come back here, the derivative of 1 was 0. I think I wrote a 1 down earlier, sorry. But the derivative of 2 over x is negative 2x to the negative 2. So what I end up with is the derivative inside is negative 2x to the negative 2. Now, if I combine that together, I get 1 over I times negative 2x to the negative 2. And so the last thing I need to do is plug in I. Remember, I was 1 plus 2 over x. Now, since I'm going to need that as part of my limit, I'm just going to write that in here. So the derivative of just the top, I haven't touched the bottom at all, but the derivative of the top is 1 over I is 1 plus 2 over x times, where the inside is negative 2x to the negative 2. Now that I have the derivative of the top, I'm ready to find the derivative of the bottom. So the derivative of 1 over x, well, 1 over x we already said was x to the negative 1, so if I just ignore the 2 here, I get the derivative of x to the negative 1 is negative x to the negative 2. So the derivative of the bottom is just negative x to the negative 2. So now that we found the derivative of the top and the derivative of the bottom, we've turned this limit into a new limit, which is hopefully simpler. But as we look at it, it actually looks more complicated. It looks like there's a lot going on. However, what we want to do here is, before we decide whether or not we've helped ourselves out at all, we want to actually simplify the problem at all if we can. So that is, what I notice here is that there's an x to the negative 2 on top and an x to the negative 2 on the bottom. So if we look at these are going to cancel out to 1, unless x is 0, but x is going towards infinity, so it won't be 0. So we can cancel those out for this limit. The same thing, I'm going to cancel out the negatives here, because a negative negative is a positive. So if I simplify this, I get the limit as x goes towards infinity of 2 over 1 plus 2 over x. Now if I look at this, this is a much simpler limit than this one is. So I have indeed made progress. It's just I had to take the extra step of simplifying because I did want to calculate what this limit's going to be. Now that I have a new limit, I start the problem all over again and I say, well, what happens as x goes towards infinity? So if I look at it in this case, the top goes to 2. 1 plus 2 over a huge number is an extremely small number, so as a limit we say that's 0. So we get 2 over 1 plus 0 is 2 over 1 is just 2. Well, 2 is a number, so we have indeed found that the limit as x goes towards infinity of x times natural log of 1 plus 2 over x is indeed 2. Another example of a limit. We're going to look at the limit as x goes to 0 from the right of x to the x. Now as we look at this, I just want to point out we're going to the right because x to the x is not defined for negative numbers. So we only want to work with the positive numbers, so we're going to come into 0 from the right and only work with positive numbers. Now as we look at this again, we want to calculate this, so we're going to plug in 0, and if we do that, we get 0 over 0. So what is 0 over 0? Well, 0 over 0 is an indeterminate form. Therefore, we're going to have to do more work because we don't know what the limit's going to be. Hopefully we can use L'Hopital's rule. but we might have to try something else before we can use L'Hopital's rule because we don't have 0 over 0 or infinity over infinity. So what else can we do? In our last one, we saw that if we had a product, we could turn a product into a quotient. So if we could write this as a product, we would be okay, but we don't have a product, we have an exponent. Well, how can we turn an exponent into a product? Well, what we can do is we can use natural logs in order to take an exponent and turn it into a product. So that's what we're going to do here is I'm going to take the natural log of the function, or the limit, and say the limit as x goes to 0 of x to the x. But if I take a natural log of something, I'm changing the problem. So I have to account for that, and I'm going to say actually e to the natural log of the limit as x goes to 0 of x to the x. So that now that e to the natural log cancels out, so we're just left with the limit as x goes to 0 of x to the x. So I haven't changed the problem, I've just rewritten it so that I can then simplify it. Alright, now that I've looked at just the top here at the natural log of the limit of x to the 0 of x to the x, what I have to do now is find some way to calculate this limit. Well, the first thing I need to notice is that with the log on the outside of the limit, things are a little complicated. So the idea is that natural log is a continuous function on this domain. So as long as we end up getting an answer out, we can evaluate the limit either inside or outside and we'll get the same answer. So what we're going to do is rewrite this as the limit as x goes to 0 of natural log of x to the x. And again, this will be okay as long as we get an answer out in the end. Now, the whole point of having the natural log was that if we have a log with an exponent in it, we can pull the exponent out as a product. So now we get the limit as x goes to 0 of x times natural log of x. Now I have a new limit to calculate, so I'm going to do that, and I'm going to see what happens at 0. Well, at 0 I get x is 0, natural log of 0. Well, as x approaches 0, what we get is natural log of 0 tends towards negative infinity. So we get 0 times negative infinity. Now, the next thing we want to say is, okay, well, if that's 0 times negative infinity, what was 0 times infinity was an indeterminate form. So we have an indeterminate form again. So we want to be able to use L'Hopital's rule, but we have a product instead of a quotient, so we have to turn the product into a quotient. So what we would do is the same thing we did last time is we're going to take the limit as x goes to 0 of, and now I'm going to pull the x to the bottom by writing this as natural log divided by 1 over x is the same as x times natural log of x. So now if I use 0, I get natural log of 0 as negative infinity, and 1 over 0 is plus or minus infinity. And so what we end up with is infinity over infinity, or a plus or minus infinity over plus or minus infinity. So we can indeed use L'Hopital's rule. So what does L'Hopital's rule say again? Is that we'll take the limit as x goes to 0 of the derivative of the top over the derivative of the bottom. So now the derivative of natural log is just going to be 1 over x. And the derivative of 1 over x is, well, we did that one in the last example, was negative x to the negative 2. So we get 1 over x over negative x to the negative 2. Now, that still looks complicated, but I can actually simplify this. So I'm just going to go off to the side and say 1 over x divided by negative 1 over x squared is the same as x to the negative 2. If I divide a fraction and I should multiply the reciprocals, I get negative x squared over x is just negative x. So what I get is the limit as x goes to 0 of negative x. Now, if I take the limit as x goes to 0 of negative x, what I end up with is just, I plug in 0, I get out 0, that's a number. So now I can evaluate this limit is 0, so therefore this limit is 0. So that is, the limit as x goes to 0 of natural log of x to the x is just 0. So we have found this limit. But remember, that wasn't the whole thing. This was just the top portion of an exponential, so now we have to go back and find the original limit we were looking for. Alright, so now if we bring it back to our original limit, we see that the limit as x goes to 0 from the right of x to the x is either the natural log or the limit as x goes to 0 from the right of x to the x. And we found that this top was 0, so we just get this is 0, so we get e to the 0. E to the 0 is just 1. So the limit as x goes to 0 of x to the x is indeed just 1. Thank you for watching. As always, I hope you learned something today, and I hope you enjoyed the process along the way. If you did, make sure to like the video and subscribe to the channel. It helps me to know which videos are helpful, and it helps other people to find these videos so that they can also get help. Thank you.